Alright, in this video we're going to revisit sort of a classic problem that we're going to sort of use calculus to go a little bit further with. We're going to look at this projectile motion problem. And, you know, there is some actual meaning behind some of the numbers here. When you take a physics class, you'll learn that the negative 16 is related to the acceleration due to gravity. You'll learn that this 96 here represents an initial velocity and the 256 represents the initial height. Those are all things that we can learn and memorize and deal with here. But really what we're trying to take a quick look at is the fact that we see a quadratic, right? That the height s, right, at any time t is given by this quadratic, and because there's a negative in front, we know it's going to look like this, right? Now, the reality is that you're going to think about this as sort of being up on a cliff. You're going to throw a projectile off that cliff or building or whatever it is, and at some point it's going to hit the ground. The reality is the quadratic function keeps going forever. It goes back in time, and the projectile of the function would continue to go through the ground, right? But because it's an application problem, there's a sort of built-in domain on top of the algebraic domains of the functions. So when you get into word problems, one of the things you always have to consider is, because this is now representing some sort of physical quantity, there might be some inherent domain restrictions you'll have to address. Now, there are really two important points in this projectile's path. Now, it has a height at any point, right? But the 2 points of interest that we usually focus on are the vertex of the parabola, which represents the maximum height. Right, so anytime we're talking about how high does it go, right, we're talking really about the vertex. And the other point of interest is, when does it hit the ground, right? And that's really the zero, right, or x-intercept. So, one of the challenges you'll have in any math class, and it may be even, related science or business or economics classes, is sort of getting from the word problem down to an algebra problem. Hopefully at that point it's easier, right? So in some ways you want to do sort of word association translations. What is the maximum height the object will reach, right? What we're really focusing on here is the vertex, okay? Now there's a couple questions we could ask you about the vertex. We could say, when is it going to reach its highest value? Or what is its highest value, okay? The t, the time, tells you when something happens, right? S of t tells you the height at that time t, right? Now in this question they're asking us to find the maximum height, right? But we can't find the maximum height until we know when we're at the maximum height. So, we usually start with the independent variable, in this case time, and, when you look at a quadratic function like this, right, you could go straight to the vertex formula. The vertex for x would be x equals negative b over 2a, but in this case we'll use t. T would be negative b over 2a. Now, every time you need to know something, that means you have to memorize it. But if you remember your quadratic formula, right, you actually have the vertex part right here, right? So if you notice, every point on the parabola has a mirror image, right, except for this one, right? And that's, at that point, this, square root becomes 0, and it becomes ignored. And essentially, if you know your quadratic formula, you actually already have your vertex formula there, okay? So in this case, the time at which you're going to reach your maximum height will be negative 96 over negative 32, right, because that's 2 times negative 16, which simplifies to 3. It's going to take 3 seconds to reach the maximum height, right? But you can't answer how high does it go, and somebody tells you 3 seconds. That's not a height. What you're going to do then is use that time to determine the height. Okay? Back to the original function. S is a function of t. Plug in 3 for every occurrence of t, right? 3, remember to follow your order of operations. 3 squared is 9. 9 times 16, right, is 144, so we have negative 144, right? We have 96 times 3, which is 288, right? And then we have 256 256. And when I put these two together, I'm going to get a positive 144. And I add that, to 256, and it looks like I get an even 400. And, because it's a word problem, we want to be sort of complete. This is in feet. Right? So we want to give feet. If I wanted to be complete, I would say 3 seconds for t. Now, it didn't actually state seconds, and it didn't actually state feet here. So I was a little bit loose in the description here. The negative 16 is the indicator that we're talking about feet per second due to the acceleration of gravity. But I don't want to get too complicated. That's something that you'll learn about later or in another course. Now for part B, they're asking us, when will the object hit the ground? Okay. Now, when you hit the ground, right, you're going to be at this spot right down here, and your height is going to be 0. Right? Your height, which in this case s, I know it might seem like h would be a better variable for height, but we often use s for position, and sometimes the letters are not intuitive, but if a letter had already been used for something else, it can't be used. When you're on the ground, your height is 0. So we're going to start by setting this entire quadratic equal to 0. Right? And the quadratic formula, again, is always an option. The numbers here are large, but if you have a scientific calculator, it's not that bad. However, it's not a coincidence, and you should always sort of at least hope that you get such a situation. You can factor a negative 16 out of this, right? And then you will get the following quadratic, right? So 16 goes into 96 6 times, 16 goes into 256 6 times. You take the negative out, and now you're looking for two numbers that multiply to 16 and subtract to 6, negative 16 and subtract to 6, because there's nothing other than a 1 in front of that t squared. So this turns out to factor very nicely. So you get negative 16 t minus 8 t plus 2 equals 0. Now there are 2 zeros for this quadratic, right? But one of them doesn't make any sense in the context of this word problem, right? You can't be negative 2 seconds, right? You can't be 2 seconds before you started the clock, before you threw the object, right? But again, that would explain this 0 that we know the parabola is going to have. So we're going to ignore this one because it's outside of our domain. It's going to take 8 seconds to hit the ground. Okay. Now in calculus, we're going to be able to do a little bit more than this, because this really is pre-calc or even algebra, depending on what it's called when you learned it. But what we're going to learn, one of the major tools in calculus, will help us identify rates of change, and we'll be able to use rates of change to figure out the maximum height. Right? But we're also going to be able to figure out the velocity at impact. Okay? How fast is that projectile moving right as it's about to hit the ground? Okay? So that's for later in the semester. Again, just trying to get used to word problems, making these associations, understanding points on a graph in relative terms to important points in the projectile's path.